let's talk about one of the biggest, most important ideas in all of physics, but one that almost nobody really understands: entropy. It's this invisible engine that governs, well, pretty much everything, from why your morning coffee gets cold to why time seems to only move forward, and maybe, just maybe, why we're even here to think about it.
So to really get our heads around this, let's start with a puzzle. We all know the Earth gets energy from the sun, right? It gives us light, it gives us warmth, it powers pretty much the whole show. But what is that energy actually doing for us? And believe it or not, the answer is way stranger than you might think. Okay, so here's where things get weird. For the Earth to maintain a stable temperature, not freeze or boil over, it has to radiate the exact same amount of energy back into space as it gets from the sun. As you can see here, 100% in, 100% out. It's a perfect balance, a zero-sum game. So hold on. If we're not getting a net amount of energy, if the cosmic books are balanced, what on earth are we getting? What is the sun's secret ingredient that allows for all the complexity and action on our planet? This is the big question. And to answer it, we actually need to take a little trip back in time to the age of steam. Right. So our journey begins in the early 1800s, smack in the middle of the Industrial Revolution. The whole future of nations, it literally depended on who had the best steam engines. But there was this one massive problem. They were shockingly inefficient. Just how inefficient? We're talking about 3%. Even the absolute best engines of the day were only converting about 3% of the heat from burning coal into useful work. That means 97% of all that energy was just, poof, wasted. A young French engineer decided he had to figure out why. His name was Sadi Carnot, and he had a brilliant idea. He thought, okay, to really get to the bottom of this, let's forget about all the real-world problems like friction and heat leaks. Let's imagine a perfect engine, a theoretical one, to find out what the absolute fundamental limit is. So picture his ideal engine. First, you have a hot source, like a fire, that heats up some gas. The gas expands and pushes a piston. Great, that's work. The gas keeps expanding and cooling down. But now, to get any more work done, you have to get that piston back to where it started. And here's the kicker. Carnot realized that to compress the gas again, you have to dump some of that heat into a cold place. You can't just recycle it all. And that was the giant discovery. Even in a perfect world, with a perfect frictionless engine, you can never, ever be 100% efficient. To get work done in a cycle, some of that energy is always going to be lost. It doesn't vanish, of course, but it becomes less useful. It spreads out, it dissipates. Now, this universal tendency for energy to just spread out and become less useful, well, it needed a name. And a few decades later, a German physicist would give it one, and in doing so, he'd basically define one of the most fundamental laws of the entire universe. And that name was entropy. The physicist was Rudolf Clausius. Now, a lot of people describe entropy as just disorder, and that's kind of right, but it's not the whole picture. A much better way to think about it is as a measure of how spread out, how dispersed, how diluted energy is. Clausius summed it all up in what we now call the second law of thermodynamics. It's a big one, and it says this: the entropy of the universe tends to a maximum. In any closed system, things are always moving from a state where energy is concentrated to a state where that energy is much more spread out. Always. But that just makes you ask another question, doesn't it? Why? Really, why? What cosmic force makes energy spread out like this? Well, the amazing thing is, it's not a force at all. It's just probability. It's a pure numbers game. Think about a Rubik's Cube, okay? There is exactly one way for it to be perfectly solved. That's a very special, very low probability state, a low entropy state. But how many ways can it be all jumbled up and messy? Quintillions. Literally quintillions of ways. So if you just start making random turns, what are the odds you're going to land on that one perfect solution versus one of the quintillion messy states? Yeah. And energy is exactly the same. It's not that nature has some deep desire to be messy. It's just that there are so many more ways for energy to be spread out among trillions of particles than for it to be all neat and tidy and concentrated in one spot. Nature isn't choosing disorder, it's just stumbling into the most likely arrangement. Okay, so if the entire universe is on a one-way trip to Messy Town, how do we explain, us? How does anything get organized? How is a building or a tree or even a single thought possible? This constant, relentless march toward higher entropy, that's what scientists call the arrow of time. It's the reason we remember the past, but not the future. It's why we see an egg fall and break and make a mess, but we never ever see the splattered mess on the floor spontaneously leap back together into a perfect egg. That would be going from high entropy to low. And statistically, that's just not going to happen.
So here's the puzzle, right? If things only get messier, how in the world you create these amazing pockets of order? How can an air conditioner make a room colder, which is more orderly? How can life build something as unbelievably complex as a human brain?
And the answer is, you can do it, but you have to pay a tax, an entropy tax. You can make your room colder, you can decrease its local entropy, but to do it, your air conditioner has to pump an even greater amount of heat and disorder out the back. So while your room gets more orderly, the universe as a whole gets even messier.
And get this, it even happens all on its own. When you put soap in water, the soap molecules will spontaneously arrange themselves into these beautiful, ordered little spheres called micelles. They do this to trap dirt. But in creating that local order, they actually allow the water molecules around them to become more disordered. The total entropy of the whole system still goes up. So here is the absolute bottom line. The second law is never broken. Ever. You can build a sandcastle, you can write a symphony, you can build a living cell. You can create these incredible pockets of order. But the cost is always, always a greater increase in the total disorder of the universe. The universe always gets its cut. Which brings us right back to where we started. Now we have all the pieces. We can finally solve that first puzzle. What is the sun's secret ingredient? What is it that Earth really gets from the sun?
It was never about the amount of energy. It's all about the quality of that energy. The sun doesn't just send us energy. It sends us incredibly high-quality, concentrated, low-entropy energy. Think of it like getting one really powerful, high-energy photon. Life here on Earth grabs that quality energy and uses it to build order, to build itself. And in the process, it degrades that energy, spreading it out and radiates it back into space as, say, 20-weak low-energy, high-entropy photons.
That flow, that constant cascade from low entropy to high entropy, that is the engine that powers everything. Every plant that grows, every animal that moves, every hurricane that forms. It's all part of this grand cosmic process of taking the sun's beautifully ordered energy and making it messier. We are all surfing a giant wave of increasing entropy.
And this leaves us with one last kind of wild thought. If the universe must always move towards maximum entropy, maybe complex things like life aren't some statistical fluke that fights against the trend. Maybe, just maybe, life is actually the universe's most creative and efficient way of spreading energy out and getting the job done. Something to chew on.